Hi everyone. Today we're going to take a look at the R2 notes, but before we do that, there's a small little section here that is on set builder notation. This is just a way of representing a set of numbers, and so the first thing you're going to notice is this curly bracket at the start at the end. This is how we denote a set of numbers. And so the way we read this is the curly bracket tells us it's the set of all. Here's our variable, x's, that's just our placeholder. Vertical line means such that, and then we have some sort of condition. In this case, it says x is greater than 0. So this is every number that is greater than 0. Here's another example right here, right? The set of all x such that x is less than or equal to 2. Okay, so we're going to be talking about sets of numbers today in these R2 notes. Okay, so the first set of numbers we're going to talk about, we're going to skip that funny looking R there, is the natural numbers. Okay, so natural numbers are also called counting numbers, right? So if you're counting your fingers or your toes or something silly like that, the symbol for the natural numbers looks kind of like a double stacked N. It's kind of a goofy looking symbol. Okay. Then we have a set of numbers that's bigger than the natural numbers. That is the whole numbers. And you're going to notice in here that the O in whole looks like a 0 because that's the only difference between it and the natural numbers is that 0 is included. Okay, and then we keep going, and now we have another set of numbers that's bigger than the ones that came before it, and that is the integers. Integers, the symbol of that set of numbers is oddly a Z. Don't ask me why. Kind of looks like a double stacked Z. Okay, and this is all of the whole numbers, including all of the negatives of the natural numbers. Okay, and now if I take two integers and I divide them, I get the rational numbers. Rational numbers, I like to highlight the first part of this is the word ratio, right? And hopefully we remember that a ratio is really just another way of saying a fraction, right? And so here, right, it says P over Q, right? I'm dividing two integers. As long as the denominator is not 0, then this becomes a rational number. And so this can look like a lot of things, right? 7 over negative 9, right? 5 over 3, right? 6 over 1 million, right? And, we could reduce that, right? Okay, rational numbers is what we get when we divide two integers, right? Again, as long as the denominator is not 0. Irrational numbers are numbers that cannot be represented by fractions. So this is the first part in this list of sets of numbers that we're not going with a larger set of numbers. So, rational numbers is bigger than the set of integers, is bigger than the set of whole numbers, is bigger than the set of natural numbers, right? Irrational numbers is not in that kind of like hierarchy, and we have a good visual in the notes later on that will help with that. Irrational numbers are numbers which cannot be represented by fractions, right? Because these are numbers that do not terminate, meaning they go on forever, and do not repeat. There's no pattern, right, that we can see that makes this number stop short. So for example, right, a rational number could be like 1.3 repeating, right? That's 4/3, right? But that works because there's a pattern there, right? It repeats those 3s, right, even though it goes on forever. Okay. Irrational numbers, some examples of those that you may know. Square root of 2, right? Square root of 3. Square root of 4 is 2. That is rational. Okay, square root of 5, square root of 6, square root of 7. There's so many of those, right? And then we get some special numbers that you might be familiar with. Pi, right? The Greek letter pi, 3.1415, blah, blah, blah. You probably remember that from your circle formulas in geometry. And then we get another number we're going to talk a lot more about later on in this class, and that is E. So if you don't know E, that's okay. We'll get to that later. 2.718, 2818, blah, blah, blah. It keeps going on forever as well. These are famous irrational numbers, okay? Now, irrational and rational, these are kind of two big categories, right, that are not overlapping, right? They're kind of like next to each other, right? But all of these fall within the category of real numbers, right? Every set of numbers that we listed above is real. If we go back to the top of the notes, right, this kind of like double stacked R symbol here, right, this is for the set of all real numbers, okay? So natural numbers are real, whole numbers are real, integers, rational, irrational, all of these numbers are real numbers, right? And so you might be looking at this and wondering, why is this called a real number? Is there such a thing as a fake number? Not exactly, but there is something called an imaginary number, right? And so you might look at that and go, that's an odd name, but really it's just a way of describing something that previously we said did not exist. Right, so an imaginary number, the imaginary number that we start with is I, right? And it's kind of like in italics, right? It's usually kind of in maybe like a cursive I or something if you want to get fancy with it. But it's just the square root of -1, okay? And so you can take this number, right, and you can multiply it. So you can have a number like 3i, right? You can have 7i. You can have root 2 times I. Now you have to be careful when you're multiplying it by something with a square root, because you don't want it to be misinterpreted as, oh, the I is inside the square root, right? So very often for something like this, you will see the I in front of the square root, even though technically these are being multiplied still, right? So if you want to put a multiplication dot in there, you can, although that looks kind of goofy. Okay, so we have these imaginary numbers, right, which is kind of the counterpart to real numbers. But then real and imaginary, both of these fall into a larger category called complex numbers. Complex numbers is the sum or difference of a real number and an imaginary number. So something like 3 minus 2i is a complex number, right? So the real part is 3, the complex part is the 2i, right? We have -5 plus 7i. I just wrote another example here of something that you might see in trig next year. Something that looks like this: root 3 over 2 minus 1/2 I. Or you could write I divided by 2 if you wanted to, okay? And then we have stuff like these two at the end here, -5 and then 7i, and you're looking at this and you're going, how is this complex? Well, -5 is a real number, but it's considered complex because you could say its imaginary part is 0, -5 plus 0i. And so every real number can be written as plus 0i, and that puts it in the category of a complex number. And then 7i, you could think of it as having no real part as well. So every imaginary number is also a complex number. Okay, now this is a lot of different sets of numbers. And so before we do the example on the next page, I really like this image right here. I put a little blue star next to this. That's something that is worth memorizing for a future assessment. Okay, so this kind of shows you the layering of the numbers. So we can start in the order we went through it in the notes. We have whole numbers. Oh, sorry, actually, this doesn't even have natural numbers, right? Natural numbers should be inside of whole numbers, then whole numbers, then integers, then rational numbers, and then side by side with that is irrational numbers. Both of those fall in the category of real numbers, right? And then we have complex numbers, but then separate from real numbers, within complex, we should have imaginary numbers here as well. Okay. So let's do a quick example here. So I've kind of highlighted these with the same colors that we used above, and we'll just kind of circle along. And so some of these numbers are going to get highlighted many times. So natural numbers, I'll do these in green, right? So these are my counting numbers, right? So I can count 1 of something, I can count 6 of something. Square root of 2 is 1.414, right? And it goes on forever. Can I count 1.414 of something? No, I cannot. Okay. Whole numbers is just the natural numbers, but I include 0 in there as well. So I'll recircle 1 and 6. Okay. Integers are whole numbers, but I include the negatives. So -8, -6. And now you may look at -12 over 4 and go, hey, that's a fraction, right? That's not an integer, but remember, you can reduce, right? This is the same as -3, right? So I will include it as an integer once we simplify it. And then 0 is an integer, 1 is an integer, 6 is an integer. And so some of these numbers you're going to see are going to get included many times. Okay. Rational numbers, I'm going to do some bulk circling here. So remember, that's rational, think ratio, think fraction, right? And so from -8 to +1, all of these numbers are rational. So I did that in the pink color. Okay. √2 is not, √5 is not, but 6 is. Okay. Irrational numbers, right? These are my two square roots, √2 and √5, right? And then every number here falls in the set of real numbers, right? And then the question doesn't ask for it, but all of these numbers are also complex numbers, okay? Okay, let's keep going. Okay, we're going to switch gears here a little bit and talk a little about computation and PEMDAS, okay? Exponential notation, right? So what is an exponent? Exponents are just repeated multiplication, right? So when I ask you to do -2⁴, that's -2 times -2 times -2 times -2, right? And when we multiply an even number of negatives, we get a positive. So this is 2⁴, that's +16, okay? N plus 2 squared is n plus 2 times itself, right? And so n plus 2 times n plus 2. Hopefully you remember foiling, right, from Algebra 1, right? We can FOIL this out and get n squared plus 4n plus 4. And this last one's a little tricky, and this is one where students make very silly mistakes, right? How is it different from the first one? The negative is not part of the exponent, right? So really, to get technical with this one, you can think of this as -1 times 2⁴ power, which means it doesn't matter what 2⁴ power gives you, your answer is going to be negative. So we get -16 for that, okay? I'm going to trust that we remember how to do some of these exponents, so we're not going to do the evaluating. We're just going to jump to D and E and talk about base and exponent, okay? So the base, remember, is the number that is getting repeated to multiply, right? So in this case, for D, it's 4 times 3 has the exponent, not the 4. So the base is just 3. However, for E, because of the parentheses, 4 times 3, your base is 12, right? And then on both of these, right, your exponent is 2. Okay? And this brings us into our PEMDAS review. We're not going to talk about all of this. You guys remember this from Algebra 1, right? Parentheses, anything in parentheses you do first, then exponents. And then the only thing I want to point out with MD and AS is the grouping, okay? A lot of people remember the phrase and they go, oh, I must multiply before I divide. I must add before I subtract. But in these two groupings, remember, the rule is actually left to right, okay? You don't have to multiply before you divide. You don't have to add before you subtract, right? So if I asked you to do, 3 minus 6 plus 4, you don't have to do the 6 plus 4 first. As a matter of fact, I say you don't have to, but really I should say if you add that first, it will be wrong, right? So this is -3 plus 4, right? You do the 3 minus 6. That has to be done first. And so this gives you an answer of 1. Okay? Okay, let's keep going. This next section, I think, is a good place for you to pause the video and try these 4 on your own. And then you can unpause, right? And we can go over the answers. So pause for a second myself if you want to pause right now. Okay, good time to unpause and let's take a look. So for A, right, and really I'm just going to post the answers. I'm not going to go too much into detail. Okay, so A, you have to do the dividing first. You have to do the multiplying after the 2⁵. So don't do 2 times 5 and then cube that, okay? And then for B, be careful, right? You do not do the 7 times 3 first. If you do 7 times 3 first, you're going to get the wrong answer, okay? For C, you're dividing, right? And really, you have the numerator and the denominator. You can think of those as kind of being in their own parentheses. And then I just kind of wrote this out for C. You know, the negative is with the 9 when you do your calculation, but really it doesn't matter where you put the negative, it's the same number, right? 13 over negative 9, negative 13 over positive 9. Or if you just put the negative in front of the fraction, then it just means the whole fraction is negative. So you can write that however you want, okay? And then, yeah, D, we just have some tricky negatives we have to be careful from. D, again, you get negative 31 in the denominator, right? But you could write that however you want. Okay, now a little bit of evaluating using some variables. So we have some variable values here, okay? For A, we're going to plug in the negative 2 for X, right? Remember, PEMDAS, you have to do the negative 2 squared first. So it becomes positive 4 times negative 4. So that's negative 16, right? Negative 7 times 5 is negative 35, right? And then 4 times negative 3 is negative 12. Add up those three negatives, you get negative 63. Okay. For B, I'll take a couple more steps for this one, right? We're going to plug in X's negative 2 first. So negative 2 times negative 5 gets you negative 7 squared. 4 times 5 gets you the 20, right? And then negative 3 plus 4 gets you 1, okay? And now again, right, be careful here. Negative 7 squared is positive 49 times 2 gets you 98. Add 20, dividing by 1 you can ignore, right? And so you get 118. Okay. Let's keep going. And now we're going to switch gears here and we're going to talk about some properties of real numbers. Okay, so this is when we're doing PEMDAS type things with real numbers, right? What are some things that we notice? Okay, the first two properties are called commutative. Okay, and the way I remember this is I think of a specific word. I think of the word commute. Okay, and now you may have heard this term before, but a commute, right? If you think about this, this is very commonly used for people that have jobs, right? I commute to work and then I commute home, right? And so for most people, that route for their commute is the same forwards to backwards, right? And so meaning if I reverse it, right, backwards to forwards, I'm going the same route, right? It's just the same roads, or if I take the train just in reverse, right? So this is something that is true for both adding and multiplying of numbers. So notice the property names here, right? It says of addition, of multiplication, right? However, you cannot commute with adding and, with dividing and subtracting, right? If I do, 3 minus 6, right, that's not the same as 6 minus 3. Right? If I do 3 divided by 6, that's not the same as 6 divided by 3, right? So you can only commute in adding and multiplying, okay? The next property is called associative. And so, again, this is specifically for adding and multiplying, okay? And the way I think of this is who you associate with doesn't matter, okay? Right? So I think of the word associate, I think I erase the A, there we go, right? Whom do you associate with, right? Well, if you imagine 3 friends, right? A, B, and C, right? If B and C hang out and then A comes to hang out, that's the same as if A and B hang out, then C comes to hang out, right? And so this is true for adding and multiplying, right? That the grouping doesn't matter. You'll get the same result either way, okay? Distributive property, right? And really, I'm going to add a slight thing to this, right? It's A times parentheses B plus C, but actually it could also be minus. So I'll write the plus minus symbol there, meaning you could do B minus C, and you would get A times B minus A times C. So in this example as well, right, if this was 2 times the quantity 3 plus 4, right, I could do 3 minus 4, and then this symbol would just be a minus in the middle, right? But distributive property, probably the one you've had the most experience with, right? It just means the 2 can be multiplied with the 3 and multiplied with the 4. Then you do the adding or subtracting, okay? But if you're just like, hey, I can do 3 plus 4 and multiply it by 2, right? Follow PEMDAS, that's totally fine as well, okay? Now we get into some interesting ones, okay? identities and inverses, okay? The identity properties, again, you'll notice this is for adding and multiplying, right? Identities are things that do not change the value, right? So A, what can I add to A so that it doesn't change? 0. What can I multiply to A so that it doesn't change? 1, right? 3 plus 0 is 3. So the additive identity is 0. The multiplicative identity is 1. Okay? Inverse is what do I have to add or multiply by so that I get the identity, right? And so for A, you add the opposite of A. Now, technically, you guys have grown up your whole life calling this just subtraction, right? 3 minus 3 is 0, right? But technically, you are adding the inverse, okay, in order to get 0, right? So, fun fact, right? Subtraction is really just adding the negative, okay? Multiplying, same thing, right? You're looking at this and you're like, isn't this just A divided by A? But division is just multiplying by the reciprocal, right? And so the multiplicative inverse, for 3, right, is 1/3. Because when I multiply those, the 3's cancel and I get the identity, which is 1, okay? Last thing, the 0 property. This is only for multiplying, right? A times 0 is 0, right? So 5 times 0 is 0, right? Any real number times 0 will get you 0, okay? This next little part just talks about silly mistakes that students will sometimes make. Basically, for the first one, right, they will forget to distribute, right? And just write, oh yeah, that's just 3x minus 2, right? Well, not quite. You have to distribute. And with the second one, right, 4x minus 8, they'll think, oh, the 4 is distributed there, right, when it really is not. Okay. Okay. Let's identify the property being used. So 4 times 1/4 gets me 1. That is the multiplicative inverse. Okay. 5 plus 0 is 5. That is the additive identity. 2 times 7 is the same as 7 times 2. Same forward and backwards. That's the commutative property of addition, technically. Okay. Or multiplication, excuse me, brain fart. 4, 3 plus the quantity 1 plus 7 is the same as quantity 3 plus 1, then plus 7, right? That is whom you are associating with, not mattering, right? So that's associative property of addition, okay? And then 5 actually has 2 properties in play here. So the first one I noticed was the times 1, right, is the multiplicative identity, because times 1 does not change anything. But then I also noticed these parentheses, right? And so you might look at this and go, hey, there's no parentheses here, right? Well, that's because the parentheses don't actually matter when you're multiplying a set of numbers, right? So the association of the 1 times 5 does not make a difference on the final result. So that's associative property. Okay. Okay. Last thing we're going to talk about is absolute value. So absolute value you might be familiar with, right? What does absolute value do, right? And what it is. So first off, the symbol, right, is just 2 vertical bars. You can do this for any real number. And what it says is if your number is positive or 0, right, notice the equal to, you just keep the number the same, right? So, what's the absolute value of 7? It's just 7. Okay. However, if your number is negative, you then multiply it by a -1, meaning what's the opposite of your negative? It's a positive, right? So what's the absolute value of -12, right? It is positive 12. That's what absolute value does. Okay. So some quick examples, right? Absolute value of -5/8 is just positive 5/8. B is interesting. The negative is outside the absolute value, so it is not affected by it. So this answer is just -8. C has a negative in the absolute value. That becomes positive 2, but there's still one on the outside, and so your final answer is -2. Okay. And then for these last two, right, we're just going to plug in some variables, right? And so for this first one, plug in -6 for x, plug in 10 for y. And now really think of absolute value as like parentheses when you're doing PEMDAS, right? So do everything inside of it first, then do the absolute value. Don't turn these negatives into positives. That's a really common mistake. 2 times -6 is -12. -3 times 10 is -30. So again, do everything inside first. Do not turn these positive yet. Okay, so that becomes -42, and then its absolute value is +42. Okay, B, very similar, right? Let's go ahead and plug it in, right? -6 becomes a +6, so that's +12, right? 3 times 10, that's 30. This negative unaffected by the absolute value, and so that gives us -18. And then in the bottom, absolute value of their product of -6 and 10, and so that's going to give us 60, -60, but the absolute value gives us positive. -18 over 60, we should remember how to reduce fractions, right? Both of these numbers are divisible by 6, and so we get -3 over 10. Okay, so hopefully we're feeling off to a good start, and I will see you all next time.